Hey, uh, our next talk is from Professor Edgar Simo-Serra. Uh, Professor Edgar Simo-Serra is from Waseda University. He's now an associate professor at the School of Science and Engineering, and he graduated from Barcelona Tech with a degree in engineering in 2011 and obtained a PhD from the same university in 2015. Before joining Waseda University, he has also worked in the Japan Science and Technology Agency, and his current research interests include computer vision, computer graphics, and machine learning, particularly in the field of image processing, with leading papers published in CPR, ICV, HCV, SIGGRAPH, and also other top conferences. So let's welcome Professor Edgar Simo-Serra. So time is yours. So I will stop sharing. Okay.
Thank you for the introduction. 1 second. I guess you can see the screen.
Wait for a while. Yeah, it started. Maybe wait for a while. Okay, now it works.
Okay. Okay, so thank you for the introduction. I'll be talking a bit about my recent research in machine learning aided content creation for illustration and games. Okay. So this is a talk that I'll talk a bit of my vision for the different things we can do with machine learning. And so up until now, lots of approaches that we've seen are focusing on these end-to-end monolithic single frameworks. So you have this big neural network that can be multitask, multiple inputs, multiple outputs. And these have shown really promise, especially in more fields of computer vision. But they have several issues, right? So they lack interpretability. Furthermore, it's hard to incorporate priors or knowledge you know about the specific problem. And when you incorporate priors, usually it is in the sense of data pre-processing, and that is not usually the best way of doing it, right? Because it gets obfuscated in the training data pre-processing, and you would like to have things usually more explicit, right? On the other hand, computer graphics has traditionally been based on good ideas embedded as heuristics, right? So famous examples would be colorization by optimization, patch match, lazy brush, etc. And it's usually a core idea that they have a specific implementation for it, and it works fairly well, but it has an issue that it's very sensitive to tuning, numbers, user inputs, etc. But it's possible to change some of these heuristics for neural networks, right? So the idea here is to try to have a more holistic view and combine these more heuristic traditional computer graphics approaches with more machine learning based approaches. But some important points are to keep explicit representations and use that to try to gain interpretability and controllability, right? And try to go sort of to the best of both worlds with a focus in more this sort of human-centric interaction paradigm. Okay. So I'm going to be introducing three recent works from two from PhD students and one from a collaborator that sort of highlight this focus on this sort of research direction of trying to tackle these real world problems and try to do it in a way that's explicit, controllable, and interactive. So this first work is this is quite at the early stage, right? So it's we have a journal paper, but it's still really just scratching the surface. But this is the idea of grammar-based game description generation, and it was done by Tsunehiko Tanaka, who's my PhD student who sadly graduates this year. So this is a much more of a video game design problem. So making games is very expensive, very time consuming, and a lot of effort is being done in Q&A testing, right? And it's really hard to iterate and work with it because everything is really highly interconnected. So if you touch one thing, 30 things break. They're also really big teams with lots of people, very interdisciplinary, and it has lots of issues, right? And so this is a bit of a old slide that I've taken from Ralph Koster, but it's in log scale. But it shows how this game is basically increasing logarithmically over time to create a game. In particular, these AAA games, right? So they get more and more and more expensive. It's harder to do things, and as you may know, there's a bit of a crisis in the video game industry. With lots of jobs being lost because they're so expensive to make. There's so much competition that they're not getting the returns that are expected, right? And so the idea is how can we try to minimize this Q&A testing, this debugging, and try to do things in a human-centric paradigm. So the objective here is, yeah, basically lower the difficulty of game design iteration in a human-centric paradigm. And the initial focus of this research is to try to generate game design language output from a user text and do this in a way where we respect the grammar of the game design. Okay, so a high-level view of sort of working with an AI to make games would be the designer would be collaborating with this games. Once you do that, you could create an instance or something from that. Then you could use agents, reinforcement learning that I also have students working on to try to balance it, see how good it is, give sort of feedback. You can then use that to iterate over and over and try to make something that is interesting, fits your design visions, is bug-free, and is as robust as possible. So here we are focusing on this first stage of how can we sort of collaborate with the human designer to try to do this. And to do that, I'm going to have to introduce something that is probably not that well known, but it's the game description languages, also known as GDL. And these are our formal grammars that are used to describe games, right? And they can be used to express all sorts of games, express the game logic and everything. And they can also be used for this automatic game evaluation. And in particular, we'll be focusing on this task of generating it. And we can see an example here that, for example, from a user description sort of prompt. In this prompt, we're discussing the tic-tac-toe game, where it's a game of a popular game known from the 19th century, blah, blah, blah. It has some rules. It plays on a 3x3 grid. One player places an X, the other places an O, and they take turns attempting to get three in a row. And this would be the sort of input we would expect, and we would want the output to be sort of the description of this in game design language, right? And in particular, this is the Ludi language. And so it would be the game is tic-tac-toe. It has two players, equipment. Okay, there's a 3x3 board. There's pieces that are disc corresponding to player one, cross corresponding to player two, and the rules are you can move it into an empty area, and if there's three in a line, you win. Okay. And this would be something we wanted to do, right? So this is a simple example to highlight it, but in reality, this is much, much more complex. And this approach is based on basically using these large language models. And the idea is that you would have your prompt with some sort of demonstration, some sort of query. And then there would be two stages. The first stage is rule decoding stage, where we want to generate the necessary grammar from examples and then prompt through iterative refinement with in-context learning. And in particular, this will give an output, which is the form of a grammar, which is a Backus-Naur form grammar, right? And this would be done in the first stage. And then in the second, this would be output to a second stage, which would then try to refine it and create the particular instance of this grammar that would represent the prompt game, right? And this would use the previous grammar designed in the rule decoding stage. And in particular, this is refined using an early parser that determines the correct parts. And then it'll iteratively try to improve it, make it more fine to, at the end, generate a grammar that is compilable, it makes sense, and it works. There's lots more details, but because of time constraints, I will not go into detail. If you're interested, please see the paper. But we can see that this gives significant improvements in results, right? So if we compare against like a random baseline, we can see it, obviously it doesn't give good results. If we have a model that tries to directly predict this through an LLM, so it tries to directly map the input prompt to this game description, we see that the results are fairly low. It generates most things that don't compile, most things that are not functional, even though the rouge is fairly high, and the concepts also do not very well align. This GGDG, which uses the intermediate grammar, which I just talked about, which is our approach, we can see it does significantly better, especially in functionality and compilability. And if you combine this with some supervised fine-tuning, you can get further results, right? And there's lots more results in the paper, but we show that this is a promising direction. And once you have this game design language, then it is amenable for interaction and improvement. And so this has a few limitations. So most of the limitations is it's bound by the LLM performance. It has extreme cost because you're running an LLM several times. And the task here is still fairly limited. We would want to do this in a much more holistic approach, which is what we'll be doing in the future. With that, I'm gonna switch completely different direction, but another problem we're tackling that is also related to games, which is that of rendering, and in particular neural scene baking. And this is work by my PhD student Xiang Zhang, who also graduates this year, sadly. And so this is a very different task, but it comes to that of rendering, right? So in traditional rendering, what we have is we have some sort of 3D data, usually mesh structure. We run it through a rasterization pipeline that gives us this direct lighting, right? And we get some sort of scene. And we have an issue that we have to compute this shading even for objects that are occluded, and then we also have to try to do something afterwards if we want to add shadows or something like that. Right? This traditional rendering has been improved significantly, right, with G-buffers deferred rendering. So we have the 3D data. We first do this geometry pass. We can store the data in this 3D buffers, right, which will contain the diffuse information, normal information, and other information that's necessary to do the shading. And then we can do this final shading pass in screen space, right? Which means that instead of having to do it for all the objects, even if they're occluded, we can do it only for the parts of the objects that are visible, right? And so we have two passes, one pass that renders objects to the buffer, and the second pass that does the more expensive lighting using the buffers, right? And so this deferred rendering is usually the general approach that is being used in most of these game engines. Uh, these engines also have to handle these shadows, and shadows, as you know, is a general global illumination issue, right? So that you can no longer treat each object independently, but each object is affected by all the other objects that can cast shadows and those sort of things, right? So the blockers and the receivers, it's a mutual dependence, and it becomes quite tricky to do. And so most rasterization-based approaches use approximated global illumination algorithms, right? So for shadows, you're going to usually see something like shadow mapping, where you render from the viewpoint of the light sources onto these buffers, and then you use that to do the illumination. The advantage of this is that it's very fast, right? But the issue is that you're only handling shadow plus the direct illumination, so you get results like on the left, where everything tends to be darker than what you would actually have in reality, right? So if you also include the indirect lighting, which is where the light is starting to bounce off the walls and affect things, you actually get things that are much brighter and much more realistic, right? And so this is a gap that you have with this direct rendering approach with shadows, which is what the game engines and things like that use. And so there's ways to improve this. So for static scenes, you can use light map baking, where you basically sort of pre-render as much information as you can about the scene, about usually the static parts of the scene. So for like terrain and stuff like that, you can use expensive algorithms based on path tracing, etc. And this can speed it up, right? So now you only have to do lookups, you don't have to do the computation, and it's much faster. But this doesn't really scale very well to dynamic objects and other things. And furthermore, it's fairly limited. It's a coarse approximation, and you can get some artifacts that appear in some corners that are not something that you want. Furthermore, there's a big issue with, for example, transparency, right? In particular, refraction, where the light is being bended through objects. Like if we have a glass sphere here, the light hits the glass. Because of Snell's law, it'll refract, and then once it hits the back of the glass, it'll refract again and go out, right? And so you have this like deformed view of the scene. And if you try to do this with the screen space approximations, they're not very good in most cases, and you get something like this, right? They can't really handle things like a sphere where you have this like curving on the front side, curving on the back side, and so forth. Right? So how can we solve this? Everyone knows that one of the best ways of doing it is through path tracing, ray marching, etc., etc. And all these path tracing based approaches, what they do is they actually simulate this light transport. So you have the light that's being sent. Each pixel, you have a light. Well, you have lots of light beams that are being sent, and then you compute how they're being bouncing around the screen. You accumulate the contribution, and you can and this is really good. It can generate really complicated effects, anything you want. But it has an issue that even with modern hardware and all these advances, even with top-end GPUs, you can't really do this very well in real time, right? You have to do lots of tricks to approximate it and do it faster, but it's quite an open issue. So the summarization of these approaches, the restoration approaches are really fast, widely used in games. They're noise-free in principle. Path tracing is physically correct, can do lots of light transportation, global elimination, but it's very slow and usually has noise because you have to use few samples. And in this work, which is a series of work where we've been focusing on trying to combine this rasterization and this path tracing in a single framework, right? So I'll talk about it in more detail, but we use G buffers that serve as an input to the model, and the path tracing is then baked into a neural network. And so we have a much faster way of handling this that is encoding all these global illumination effects, right? And so the idea of this neural global illumination baking is that you have your 3D data, you rasterize it into the G buffers, right? Like your normal game engine. And then these G buffers are input into a neural renderer, which is trained with a particular scene, right? And it's incorporating all this global illumination. And so from this G buffers, it predicts the global illumination images and it outputs that. And so this is a basic concept. I'll give more details, but you have these G buffers, neural render, and now you have this final effect. You can have different, here there's two objects that are refracting, and it can handle that. And yeah, here's another example. You can see that it can model different transparent objects and also handle them to do that. And this has an issue though, that when we're straight baking it so that it predicts from the G buffers this final result, the G buffers have an issue that they are not going to provide accurate information on the refracted area, right? Because we have to, you have lots of deformation, lots of things like that. And in particular, since you're trying to map this diffuse signal, which is being deformed and can be high frequency, the neural network has a hard time encoding that high frequency data, right? And here you can see an example. The right would be the ground truth, and on the left we can see that the model sort of breaks down when it's trying to map this high frequency data through this multiple refraction and being baked in a neural network. And so there are other works that try to do this. So for example, active exploration, what it does is it does the sampling in a certain way that is being biased. And so it can get much more better results than compared with uniform sampling, right? Active exploration gives more results that are close to the ground truth. And of course, path tracing with denoising is one of the more standard approaches where you run a path tracer with very few samples, so it's relatively fast. And then you run a neural denoiser afterwards, right? And so this would be an example. That one of the issues that it has is that for high frequency and distorted signals, a denoiser can over smooth it. And so here you can see that in the ground truth with not too many samples, so it's a bit ugly. But here you can see that there's high frequency information and the denoiser just flattens it out. And so here I'm going to introduce our previous work and the new work. So in the previous work, what we did is we had our neural net, we would rasterize the G buffers, And then what we would do is we would render, we would treat all the transparent objects separately. These would be rendered in separate buffers. These would be accumulated in a sum. Why do we use a summation? Because this breaks the dependency on the ordering. And so by summing the features, which is similar to models like PointNet do, we can ensure that the transparency is order invariant. So you don't have to worry about rendering in a special, doing depth ordering, depth peeling, or rendering in a specific order. And we can do that in an order invariant way. Furthermore, this is a linear computation time with the number of objects, right? And so the global scene, the static non-transparent objects get rendered in one model. Each separate transparent object is rendered separately in a different model. They're summed up, they're combined together, and they're finally joined in a final rendering pass, right? And this will render the object, okay? And so this work uses a different G buffer. So here you can see different examples of G buffers where the normal position, the position in the scene, the albedo, roughness, etc., are captured. The transparent objects are run through networks and summed, and then finally we can train this to try to represent the ground truth. And so this neural network will learn how to handle this multiple transparency and this ordering at the same time. Here we can see comparisons. This is a ground truth. We can see zoomed in on several areas, and we can see that our approach is able to capture these fine details, while other approaches like active exploration is unable to capture these fine details. However, the main issue that this work has is that while it can handle it with some refraction effects with high frequency information, we can see the high frequency information here gets lost. And so we decided to work on trying to improve this, and we designed a new model. And this model is very similar to the previous one, but the main point here is that instead of predicting directly the color of the output pixel, what we're going to do is we're actually going to predict the UV coordinates in texture space. And we're going to use that with bilinear interpolation to get the refracted texture and use that in the neural render, right? So this neural render is going to be doing texture lookups. Well, our model is going to have explicit texture lookups, which means that it no longer has to learn to encode high frequency information, but it can make use of the low frequency mapping, right? So it learns the UV coordinates, and then it can do the lookup to capture the high frequency information. And so this is very similar in design. It uses a sum of latent vectors to get the order invariant, but it has an explicit UV coordinate lookup in the middle. And so now the model only has to learn low frequency mapping, which is much more beneficial in general. And so here we can see that we would have our scene, we would be rendered in these G buffers, then we would compute, we would predict the UV coordinates, we would do binary linear interpolation, use that as an output, and then the final neural network would combine all of these sources of information to do the final one. And here we can see left ground truth, our approach, we can see it can capture it very close to the ground truth. The GlassNet, the one without, that's doing a direct prediction. It's not using a UV lookup. It fails to capture the high frequency, and active exploration just fails completely, right? And for another scene, the same way, right? We can see it's able to capture this high frequency information much faster, much better, much more accurate than other existing approaches. And furthermore, my student's still working on this a bit to integrate into game engines, but this can be easily integrated into modern renders. It's implemented in C++ CUDA with OpenGL. It can get 55 FPS at 256 by 256, and using a super sampler, you can stick near 30 FPS with implementation. But it still has one quite strong limitation, that is it's unable to handle internal reflections, right? And so this is, and also the resolution is an issue that these neural networks, we have to make an effort to try to make them faster for these real-time applications, and also implementation-wise to try to get higher FPS at higher resolution. Okay. But that was another direction of rendering. And now finally, something that I've always loved a lot, which is the sketching. And in particular, this is joint research with Yotam's group and Adobe, and it's on parametric sketching. So this is a bit different from talking about rendering and game design, but this is about illustration. So when people draw, usually they work, especially in more Japanese animation style. You're going to do a rough sketch. You're going to then clean it up to line art. Then you're going to usually do some sort of region segmentation or some sort of flat coloring, divide the regions by flat colors, do a flat coloring. From there, you'll go to the final color and start to add a bit of gradients, and then you'll finally focus on the more details. So I have research that focuses on all these different areas, but the sketching always focuses on the first part, okay, which is how can we convert this rough sketch into a clean line art. And so this is a really, really challenging task, especially when you want to do vectorization, which means that the output is now vector. So you're converting these pixels into sort of a parametric representation of strokes, right? And existing works has issues with fidelity at dense stroke regions, right? And here you can see different approaches, and they all tend to suffer a lot. And some do better, some do worse, but it's still very challenging. And also a big issue here is running time. Many approaches take on the order of minutes because you have to sort of, in most cases, you build up a graph and then you have to optimize the graph and finally output the lines. And it is a bit of an engineering task. And here the proposed approach not only gets higher vectorization fidelity, but also keeps the running time fairly acceptable, right? So we can see that in this example up here. Our approach gives the best performance while having a running time on the order of a few seconds compared to other approaches, which can take several minutes. Right? So in particular, in this example, would be 4.5 seconds for this quite challenging drawing. And so this approach not only has this high fidelity and this fast running time, the algorithm is also fairly straightforward, and also it supports interactive refinement, which I won't actually talk about much today, but yeah, there is an entire interface where you can edit this and manipulate it in real time to improve the results. Okay. And so this work is quite complicated. It's divided into three stages, which I'll talk about right now quite briefly. Right, so it's a center line encoding, line reconstruction, and this post-processing to try to improve them. So the center line encoding, the idea here is that we're going to have this sort of input image. We're going to convert this into an unsigned distance field, right? Which can be done with a neural network. You can predict from this raster image this unsigned distance field. And then from there, what we want to do is we want to predict different information, which will be then used as parts of the algorithm, right? So in particular, we'll try to print in the different key points that there are in the raster image. We'll also predict, I'll talk about in a second, but undersampling maps, so areas where we're seeing aliasing and we want to improve it, and also the center of the line, right, which is going to be this unsigned distance map. And we'll predict these with a neural network that will be convolutional and we'll be doing in the raster domain. And once we have this, we have to change this into some data that we can use to reconstruct this model algorithmically, right? And so this is going to be a separate neural network that's going to reconstruct the initial vector paths. And then they're going to be predicted so that we can finally refine it in the last stage, right? And the last stage is going to be based on a dual contouring algorithm with downsampling and line grouping, which is going to refine this vectorization and give the final vectorization, right? So this is really technical because it is something that accuracy and doing things correct is really important. And so you can't just do it with a neural network and just let it be, right? Because it will never get the performance that people need actually in practice. Okay, so this is formulated this sketch vectorization. The main point here is we're formulating as an implicit surface reconstruction task, which is based around the dual contouring method, right? And so the idea here is we have this target vector sketch, right? That we'll see this we'll have our training data, which is going to be vector in this case, right? And we want to try to reconstruct this as accurately as possible. So in the first stage, we're going to, from this rasterized version of this, we'll try to predict the center light, this under sampling map, and the different key points. And so in here, the key points would be the endpoint and this intersection point. This would be a closed loop. And then in the second step, we're going to predict from this information up here, these sort of edge flags, which indicate if there is a crossing on, so, so this is going to indicate if there's a crossing of a line between these two pixels. I mean, each block here would be a pixel, and the green one is horizontal. And also this edge vertex, which indicates where the location of the line. And so the top, we can generate this from the vector image, and this is going to be used as a ground truth for training our distance field prediction neural network. And the bottom one, this is going to be used as, we can generate this from the vector information, and this is going to be the ground truth for the line reconstruction network. And so to do this, the data set will just use vector sketches from the quick draw and creative sketch. It's about 500,000 raster sketches here, and we can also for example, do some slight data augmentation. So render this this vector images as calligraphy, different types of markers, inks, pencils, etc., to try to make it robust to different things, right? And another thing that's important here, so in this task, accuracy is actually really, really, really important, right? And we're talking about actually sub-pixel accuracy if possible. And so to do that prediction, what we actually do is we work at a higher resolution. So we take the input image and we're actually predicting at twice the resolution and then and downsampling and doing it. So internally, it's working as twice the resolution of the predicted model, right? And so you'd see something like this. If you look at this, you can see that this is very ambiguous at this really low resolution, right? So lots of lines are being lost, dropped, and these two areas, it's basically information is being lost. And so this is actually going to be marked as this undersampled region, and we'll try to predict this undersampled areas. So areas where we'll be seeing aliasing. And we'll try to use that to refine these undersampled areas and improve it with higher fidelity. Right? And then once we have that, what we do is we adapt this neural dual contouring and apply a different set of modifications, particularly for 2D vectorization tasks, right? So there's lots of technical details here. Please see the paper. But the main idea here is we're going to be working on these 4x4 grids, right? And so from an input on signed distance field, we'll be running it through this algorithm, predict different, do these multi-size grid convolutions, run through algorithm, and we're going to predict these edge flags, right? And this center, the edge flags are going to be trained with this cross entropy and skeleton sketch skeleton loss, and L1 loss to predict the center in each area, right? And this is going to then give us these regions that we can build more algorithmic, right? And so, for example, if we have these predictions here, right, we can see that there's an ambiguity here, right? Because we have two lines that are intersecting here. They're not going there because of the flag mask. We can't regenerate the original one. And so what we can actually do is, since we know that this region is undersampled, we can separate these two so that they don't cross over there, and then we can do some post-processing algorithmic heuristically to correct this. And this is really important because there are lots of cases in long drawings where you actually have this as a limitation, right? So if you have a lot of lines that intersect at one point, other approaches are basically going to have lots of issues because you have really, really, really heavy anti-aliasing at the center, right? Oh, well, not anti-aliasing, really heavy aliasing that's happening, right? Because drawing lines, they have infinite signal, you're always going to have aliasing, and it's how you solve it, right? And we can see that existing approaches fail completely in this case. And our approach, because it'll mark this entire area as undersampled, and then it'll try to heuristically rebuild this region, and it'll give us a much better result. And so we compared on this Yan et al. Benchmark, which is a quite big benchmark for this sketch vectorization and simplification. And we can see that in chamfer distance, this is logarithmic scale, we get significant improvement at all resolutions compared to other approaches. And furthermore, the running time is significantly lower and it's significantly faster than all other approaches at all resolutions. Again, this is logarithmic, so this is one order of magnitude roughly in both performance and running time. There we can see examples, right? So for this input, here it is a zoomed in example. We can see existing approaches fail. Our approach is able to reconstruct this almost perfectly in this case, right? And we can actually see that the separate strokes that we've identified also fit this really close to the ground truth. And compared to other approaches, we can see that the details are conserved much better and that it is much faster in time, right? And this is another approach. This is an example on rough sketches. In this case, it does break down a bit, but that's mainly because you would have to train the nice unsigned distance field to remove this tone if you want to, right? In our approach, it doesn't do that, and so it fails on that a bit. And more results on rough sketch. So here we can see compared to other approaches, our approach is able to recover much more of the object than other approaches, right? And we can see that the speed time, it's quite fast, and we also have really good performance in this. And again, other examples on rough sketches where we can see we can recover many of the strokes, even in this challenging example. And I am not going to go into details today, but our approach is also interactive, so you can actually recover and correct this interactively with an interface because you can directly manipulate the edge masks and the other aspects of it. And again, other very complicated examples, our approach is able to reconstruct these quite well and recover most, if not all of the strokes. And so limitations, there's a lot of issues or room for improvement. Even though we've significantly moved the state of the art in this field, it is still really, really far from actually being used by anyone because artists are really, really picky about the results. And yeah, it's still a while before they'll be happy, right? But we can see, for example, in this input line, which is quite rough and quite complex and dense in these different areas. If we look at the output of direct output of this, we can see there's lots of noise. If we do 2x downscaling, we can see it's a bit better. And if you use line extraction, you can see it's a bit better. But in general, this rough sketches are still an open problem. We would need much better algorithms to extract this unsigned distance fields from them. And in general, so what is a rough sketch? What is lines we want to keep? And so on. It's an open problem that I do think there's no solution other than to do this in track. And so with this, I want to wrap up a bit. So I talked about three different fields. They're all, well, three different tasks. They all share the same concept of trying to make it interactive, human-centric, try to work with existing knowledge we have about the problem, and see parts we can replace with machine learning and parts that we have to keep heuristic or more traditional to keep it explicit and put it together. So I talked about game-based game description, sorry, not game, grammar-based game description generation. So this is a step towards more high-level interactive game design. It's still very hard because grammar representations are also good grammars for describing games is also an open problem. And also generating grammars with LLMs is quite tricky, but we show that by using a two-stage grammar approach, you can actually improve significant performance, right? And still yet to see how much it can be made more interactive and also see if it can be made easier to iterate over, right? So neural seam vaping shows promise in bridging the speed gap between path tracing and deferred rendering, relies on rasterization input. It can do transparency, refraction, and basically almost all global illumination effects. It does have a few limitations, and lots of room for improvement. And in particular, what my students is working a lot is trying to integrate this into game engines to actually show real world examples and real world cases of it run, right? But it still has a lot of area for working. Parametric sketching, again, approximating unareas, so this key points, undersampling, center line, unsigned distance fields, all these things that you would have to specify or your algorithm would have to like predict. We can approximate this with neural networks and stronger machine learning based approaches. And then we can use a heuristic and algorithmic based approaches using knowledge and our understanding of what line art or lines should be to try to generate it in a much more accurate way, right? And in this case, post-processing and interactivity is quite important. And this is enabled by having explicit representation of the different parts of the approach, right? And so again, keeping this explicit and interpretable intermediate representation or a final representation makes it important for that. And some of the references here, but if you're interested, you should definitely look at the papers because there are much more details that I skipped over there. So thank you all, and I'd love to take questions if you have any.
Okay, thank you, Edgar. A very nice talk. So I also have two questions. So actually, for the first one, I'm very interested in the neural scene baking. Actually, one of my colleague is also working on this direction.
Hmm.
So I think in the work you presented, you mentioned that you can learn uh, like the global illumination or something like that using
Hmm.
a network. So I'm wondering how uh, whether the network keeps the physical correctness. So I mean, how the physical constraint can be guaranteed in the learning process. Is there
Okay.
any ways to control this?
Okay, so you have no guarantees, right? Because in this case, the neural network is doing the final step, right? So it's predicting the final color, and so you don't actually have an optimization process on top. And I
Hmm.
don't think there's any way you can guarantee the physical correctness without having to do like path tracing at the end of the day, right? So I mean, the only thing you can do is work on try to train the neural network better, have better performance and stuff like that. But yeah, in general, you have no guarantees, and I don't think there's any way to incorporate guarantees in this because it's really hard. Like the rendering equation is not something you can validate easily.
Oh, okay. Okay. Actually, there a following question. So if, for example, if we can generate a lot of data, I mean, containing all kinds of illumination, like all kinds of phenomena of like refractions or something like that. So suppose there are a lot of data. Do you think we can learn a foundation model or something illumination or foundation model for the rendering? Just an open question. So like for example, right now, like for 3D generation previously, because I work on partly on the 3D generation, right? So
Mhm.
before, I mean, last year, like, or even for the video generation, we think it's hard to generate a consistent video, right? And also for 3D scene, it's also very hard for the generative model. But right now, so but with growing of the 3D data and also like the like for the neural scene baking, as long as I don't know whether if there are enough uh, a large amount of data for the illumination, whether we can learn a foundation model or what. What's your opinion? Or what's the main challenge for learn such a network?
Okay, I'm going to give you three answers. Okay, so the
Hmm.
first one is theoretically yes,
Hmm.
right?
Okay.
Uh, the next one would be that in practice, probably not, right?
Why?
Because it's a really complicated problem. You have lots of different things you have to handle, lots of different. I mean, you would have need so much data and such a big model that's hard. And my final answer is that in real time, never.
Yeah. Okay.
Yeah, I mean, I don't think in real time you could learn a foundation model and run that because if you could learn a foundation model, it would have to
Mhm.
be so big to capture so many parameters and stuff like that that I don't think it would be fast enough, right? Because speed
Yeah.
is a really big bottleneck. And one of the reason performance is actually not that good is because we're trying to keep it real time. So we
Mm-hmm.
want to keep it over 30 FPS at
Oh,
a
yeah.
decent resolution.
Yeah.
And say you want to do 4K, right? It's like even if you're generating at like to do you're like upsampling 8 times, which means you're
Uh-huh.
generating at 512 by 512, but even generating at 512 by 512 in real time in under 30 milliseconds is not something very trivial to
Yeah.
do, right?
Yeah.
And
Okay.
so
Okay. Okay.
I think the one of the main issues is so how to implement this to be very efficient, to make it much more efficient. And I think
Mhm.
that the main directions that are important here are how to train it very fast, right? So to be
Mm.
able to train it for lots of scenes. And I think another direction is how to blend it, right? So I don't think you'll
Yeah.
be able to have a single super model that does everything, but I think that you'll be able to have small models that are really good at one scene. And then what you have to do is you have to learn how to detect or how to work with switching from one scene over another and stuff like that, and doing that in a really efficient way, right? Because one of the issues is that if you actually want to learn this or whatever, you would want to be able to learn this in like 30
Mm.
minutes, right? Or 20 minutes. So a designer could
Ah,
create their
okay.
scene, whatever, train it in 20 minutes, then you can play it, test it or whatever, and then you can modify it a bit and do it over, right? If it takes a day, that means your iterative design and stuff like that can be really, really slow, right? So we have to I think it's always going to be small models, but we're going to have to
Hmm.
just learn to train them in like 20 minutes or
Okay.
10 minutes if possible, right?
Okay. Cool. Okay. I also agree. I think it's very hard to learn a foundation model. Actually, considering the lighting, different kind of lights, and some other
Yeah.
physical phenomenon. Yeah.
And especially with
It's
refraction, right? If you have multiple
yeah.
refraction, multiple effect, and we haven't even started talking about volumetrics, right? Which is
Yeah.
still an open topic, right?
Yeah. I agree. Yes. Okay. Maybe the last question is about the first part, the
Mhm.
game-based uh, game description generation. Actually, and also their a video from NVIDIA, they show that they can generate the interactive video games like in real time. So, but it's only a demo, right? So, and
Mhm.
also a very small. So I'm wondering, so what's the current challenges? I mean, right now in or using the ML tools or the learning tools to the practical game pipeline. So because normally it's very hard to design a very fancy games. So but there is a trend to using generative model to do that, e- especially for the interactive gaming. So what do you think the main challenge right now? I mean the
Okay, so I'm really skeptical of generative models, right? I really think they're not a good direction, right? So I mean, I know lots of people disagree with me, but I really think that generative models are a dead end. And I think that the interesting, so this work is mainly focusing on high level, right? It's how can we make interesting game designs that are sound, technically sound and like testable. Another issue is how can we make it look good or how can we generate the UI from that and stuff like that, right? And I think that's
yeah.
another direction that I would like to focus on, but that's much more future work. I'm more interested in the like what makes a game fun, how to make it fun, and how to iterate over that, right? But in
Okay.
the like generating a game, I do think that one of the main issues is to have it controllable. And when I mean controllable, I don't mean playing around with a prompt until it's not that bad. I mean actually having something that an editor can like model or modify and stuff like that, right? So I think that instead of trying to do it end to end, like you prompt and you have your like playable game or whatever, which I really don't think is interesting at all. I think that
Mhm.
having something that at each step you'll have like a grammar that tells you how the game is, how it plays, then from there you'll have this what assets, whatever do we need, and from there like what content, what do we do? From there you would have okay, how do I generate this content? And there would be more than like generating it end to end, you would have okay, I want to generate this model. How can I generate it so it's low polygon, it's fast rendering, it looks
Uh,
good? How can I modify it? Well, maybe you can generate it and then modify the texture, the UV mapping, or stuff like that, right? And so I think that integrating it more with existing tools. And there's lots of areas that people are not working too much, but could be automated, like UV mapping and stuff like that, doing good UV mapping, doing efficient polygon designs and stuff like that is an area
yeah,
that
yeah.
would be good fully automated. But I think that other areas you still want to keep it so that the designer, whoever's making the game, has full
Mm,
creative control and can make these key things and key points, right? And I think that it's a really hard problem, and it's not actually a one problem. It's like thousands of small problems. So there's a lot of room for improvement. But I do think we're really far away from anywhere near that at all, right? And I do think that some areas will probably see more development, like NPC design to some point
uh,
will
mm,
has more room for improvement, but I do think that these LLMs and these generative models in general are less useful than people give them credit for, right? And so I do think that we probably do have to, like, you can use an LLM or whatever like we do, but you'd probably have to generate some sort of grammar or finite state machine or some sort of intermediate representation that is interpretable and easier to work with than just
mm.
have the user interact with an LLM, which is probably not the experience they're looking for.
Yeah, actually, I agree that actually, for the people in the industry and also from the academic, they have different opinions. Normally, I know for the gaming guys, they are very critic about the design or and other stuff. Yeah, as you mentioned, the sketching things. Okay, great. Thank you for your great talk. I think our session will end here. And thank you all the audience. So thank you all for watching. So have a good night. Edgar. See you.
Bye. Take care.